Hi Sri, I am Ian Lee and I am glad to introduce you my video project here. And first of all, I'd like to introduce you the structure I chose, which is a pedestrian bridge, and it is located in Harbour East Plan, Docklands. And the dimension here I labeled already, and here is the specific dimension. And for the first part, we are asked to analyze the reaction force and to draw the ice shear force diagram and the bending moment diagram. First of all, we assume the point load and the distribution load, which are 6.65 kilonewton and 6.65 kilonewton per meters respectively. And here are the procedure I analyze the reaction force and use the data from here I calculate. I can draw the shear force diagram and the bending moment diagram. And for the sign convention here, we get the moment, and the moment is this one, and this one is useful for the later calculation in the maximum deflection. And for the second part, I first calculate the centroid and the moment of inertia. As a simple support beam, the cross-section of the beam is rectangular, so it is easy to calculate. And the centroid along the x-axis is 0 because it's in the middle, and I set the y-axis in the middle. And the centroid along the y-axis is exactly half of the height of the beam, is 65 millimeter. And for the moment of inertia, we can use this formula to calculate, and we get to ix and xy, ix and iy respectively. And it is clearly that ix is much smaller than the iy. So we use the ix here to calculate. And the max deflection, here is the formula, and we wish to calculate the slope and the max deflection. And the slope is the integration of this one, and the deflection is double integration of this one. And in the calculation, we use the distribution load here, and here is the process of the integration, and this is the process we use to determine the C1 and C2. And we assume the point and get the x and v value, and we can get the C2 and C1. And once we get the C2 and C1, we substitute this into the equation here, which is lead to here, and then we get this final formula. We can use them to determine the maximum deflection. As the maximum deflection, it occurs at when the x is half of the length of the bridge, which is 4.95 meters. So we bring it into the formula, and we can get the final value. And for the E is 200 gigapascal, and the moment of inertia is we calculated before. And this is the final answer for the maximum deflection. And for the slope, we assume there's a point B from the left side of the bridge is 2 meters, and so we get the x is 2 meters. So we can bring the 2 meters into this formula, and we can get the slope here. And at the same, the Young's modulus and the moment of inertia is the same as the maximum deflection. And the next one is the bending moment. For the bending moment, we also have a formula here, and this is the bending stress, and the M is the maximum internal moment, which is we calculate before is 82, and the C is the 0.065 meters, and the I is the moment of inertia. And for this one, we have to convert the unit to get the correct answer. And the next one is shear stress, and the same. Here's the formula, and the V is the load here, and we also have to convert the unit to the international units, so we can get the correct answer. The A is the area of the shaded area, and the Y is half of the height of the bridge, and this I the moment of inertia, and this is the final answer. And too convenient, I didn't I just calculate the maximum bending stress and the shear stress, because if we want to calculate, we have to locate a point here, and I think it's more convenience here. And the final part is the maximum principal stresses and the in-plane shear stresses with failure plans. And here's the formula from the lecture for the principal stress and the in-plane shear stress. And we have the data from the previous calculation, and we can just substitute this data into the formula, and here is the answer. And for this one is 0 or the 8.476 something, and here's the failure plans, and this one is because the sigma x and sigma y is 0, so the in-plane shear force is plus or negative of the stress here is plus or negative 0.22171 something, and the unit here is we use the same as here, because the calculation is not changing the unit here. And here's the failure plan of the same. And finally, this is the key results, and I collect them here and to make you can let you to check it from clearly. And finally, in the conclusion, I think this task is not too hard, but I spend most of my time on the maximum deflection and the slope, because it has a lot of calculations, and I also stuck on the maximum principal stresses and in-plane shear stress, because at the beginning I don't really know what are they, and then I look at the lecture recording and to find it on the lecture notes, and I copied the formula from the lecture notes and to calculate. So, but it is really helps me to improve my problem solving ability, and this is really important. So that's it. Thanks for listening and watching.